All right, hello everyone, and welcome to the online video for this week, where we're going to continue on looking at developing strategies for computation with multi-digit numbers. And so let's jump in and take a look at what this video is going to entail. First, we're going to start with some online expectations and suggestions for how to interact with this video and what you'll be needing to do after this video is done. And then the content focus of today, is really on multiplication and division with multi-digit numbers. In our last class, we were looking at addition and subtraction strategies and algorithms. And so we're just going to continue that on with multiplication and division. So a quick recap from what we were doing in our last class on computational fluency is we looked at a three-step pedagogical process trying to move from concrete to abstract. So we looked at starting with students with physical things, just hands-on things when we could with direct modeling. You may recall with addition and subtraction, we mainly looked at base 10 blocks and different types of physical drawings. We could do that. Of course, we can use unifixed cubes and things like that as well. Base 10 blocks work well for multi-digit numbers. Then step 2, we did the reasoning strategies, just looking at making sense of things, trying just lots of ways to make sense of computation. So looking at different types of strategies and visuals. You may remember we did the empty number line a lot, talked about partition and compensation strategies. And lastly, we looked at one strategy that's helpful, often a traditional algorithm strategy that is widely used in the US, and looked at that and tried to figure out why that works and how to explain that in terms of base 10 language that made sense. So we're going to do that now again, but do with multiplication and division. So to start here, let's start with multiplication. So I want you just to pause the video for a second and basically start with the question 24 times 5. How many different ways can you think of doing that? Either written out in paper or in your head? Can you think of a few ways? So go ahead and pause the video and write down a few ways how you might do 24 times 5. All right, well, no matter how you did it, let's take a look at what you did and a few of the ways here. And let's, as usual, approach it through a context so we can think about it in terms of a context. So here's our context for this first part of the video. There's 5 teams in the Youth Football League. Each team can only have 24 players. What's the most number of players possible in this league? Well, again, before we jump into just doing the computation and getting the answer, I encourage you as a teacher to really emphasize the role of estimation and to have it with the benchmark estimation. For example, we could ask students before we start, do you think that's going to be more than 100 total players or less than 100? How do we know? Do you think that's more than 200 or less than 200? How do you know? Again, estimation questions focus to stop, to make sense of the question, and to use some mental skills to think what's reasonable in this question. So we might realize that maybe between 100 and 200 makes sense, or just thinking through it that ways. But let's go ahead and take a look at different ways to approach a question like this. And let's start with the most concrete ways. Let's start with direct modeling. If we were in class, we could take out the base 10 blocks and build this out. But I want to show you, again, how to use this with online manipulatives. We're going to learn one site for online base 10 block manipulatives, and there it is on the screen, www.coolmathforkids.com/manipulatives. So go ahead and type that in your browser and go there. If you need to pause the video, that's fine as well. I'm going to go there now as well. And so when I get there, it has a choice. This site has a few choices. We're going to use the base 10 block choice right here in the middle. And just learning to do this. This is a nice site here. I'll show you what to do. And then again, pause the video and do it yourself. Kind of learn about how to go here. So we're going to build some football teams, 24 people on a team. And so what that might look like is building a team kind of like, this here. I could drag down 2 10s and 4 1s, and I've got 24 players here. The nice thing with this manipulative tool is if I just use my mouse and circle the blocks, they're all highlighted. On the left side, there's options. We have ungroup blocks, group blocks, duplicate blocks, and so on. And this one, I'm going to duplicate it, and look, there's my second team. And I can hit duplicate again, boom, and there's my third team. And I can hit duplicate again, and there's my fourth team. Getting a little bit of wiggle there from my mouse. And do that again, duplicate again, and there is my next team right there. So now I have 5 teams of 24. Now again, we could just count these up and 10, 20, 30, 40, 50, 60, 70, 80, 90, 100 and count them up and we'll get 120. But of course, we can always trade in blocks as well or group them together. Here's some nice things with this website. Again, there is a site over here on the left side for grouping 10 blocks together. So if I just circle a bunch of the same kind of blocks, for example, if I circle all of my 10 rods here and go around, if I hit the side on the block that says group 10 blocks together, oh, look at that. It just grouped those nicely into a group of 100. And if I group all of those together and hit the button on the left, group 10 blocks together, oh, look, it's kind of cool. So it does it for me here, and I can click off. And again, any way we do it, we can take a look that 5 groups of 24 is 120. Good. So again, that's direct modeling here. Now, another way to do direct modeling, kind of a visual way without doing all of the base 10 blocks as well, is a tool called base 10 grid paper. And this is where if you had a chance to print that, there's a piece for you. If not, I'm just going to demonstrate what it is. But for homework and things, you can just use it digitally as well, although if you can print it, I'm sure it's always easier to do it that way. But let's look at that for a second. So we're going to look at 24 times 5 using base 10 grid paper. And so here, this is base 10 grid paper. It's called base 10 grid paper because, well, it's 10. Every grid is 10 by 10. So everything is grouped into tens here as it goes through. And we're going to look at 24 times 5. So in doing that, again, what we're going to do is use an area model for that. So on one side of the paper, we might count out to 24. 10, 20, 4 would get me right there. And on the other side, going down, 1, 2, 3, 4, 5 would get me right there. And so we can see, again, it's 24 kids on a team, 5 teams, and an area model would look something like this. So I have 24 across the top and 5 coming down. And if I just use a little color, this represents the area of 5 groups of 24 or 24 groups of 5. And to get the answer, then it's nice because it's grouped into groups of 10s, we can count it very easy. Like in this first section here, it's 10, 20, 30, 40, 50. Well, 5 groups of 10. And this one here is also 5 groups of 10 over here. And here, again, we could count it up different ways, but basically we have 5, 10, 15, 20, or lots of ways. And again, we put those together, and we see that all together we would have 120 players on that team. This is called base 10 grid paper, and it's just a nice way to visualize it pictorially in a little different way. So that's what direct modeling might look like. All right, so then, we want to make sense of it using reasoning strategies in different ways, and this is where maybe in the beginning when I asked you to do it yourself, maybe you thought of a few ways to reason it out. And again, in our book, Van de Walle talks about 3 types of reasoning strategies kids might use. We have complete number strategies, partitioning strategies, and compensation strategies. So let's look at those. So one by one, let's take a look. Let's take a look at complete number strategies. Well, this just means that kids who basically realize 5 times 24 means like 5 groups of 24, and they're going to add them up. They might do it kind of a long way, adding it one by one. They might group them together and realize we could do this 48 plus 24, or different ways there, or even add up the 20s first. 20, 40, 60, 80, 100, 104, 108, 112, 116, 120. But basically, it's students that are really looking at it as those groups of the whole numbers and thinking of strategic ways to add that up. A second way is partitioning strategies, which is always breaking numbers into more helpful parts. And we talked about in class, the visual for that is a nice break apart method, we called it. For example, we could break apart that 24 into 20 and 4. Oops, 20 and 4 up there on the top. And that allows us to, do 20 times 5 to get the 100 in that box, and 5 times 4 is 20, and again, we get that 120, and that partitioning method in that box is a helpful way to do that. Again, don't worry about it being proportional. It's just meant to be a structure to help with that. And lastly, we have the compensation strategies. And this is where, for example, we're going to round and adjust. For example, often we like 25s better than 24s, because we think of quarters. Maybe I think, well, I don't know 5 24s, but I know 5 25s, because that's like 5 quarters. That'd be like 125. but that'd be one group too many of 5. So if I subtract 5 from that, I should get the right answer. So 5 times 25 is 125, minus 5 is 120. And it could also look like this. Multiplying by 5 is not as easy as multiplying by 10. This is a common strategy for 5s, is double the 5 and make it 10. So like 24 times 10, well, that's easier. This is 24 with a 0 on the end, that's 240. And then because I doubled the 5, I have to half the answer. So half of 240 is 120. So those are 2 examples of compensation strategies going through. And here we see our 3 types of reasoning strategies. So take a second and look at these 3. And I'm going to ask you to pause the video for a second and just look at these 3 and ask yourself, what kind of strategies are these students using? So go ahead and pause. All right, yeah, if you looked at it, you should have seen that in the top one, it looks like the student there decided they'd rather work with 30 than 27. So they did a compensation strategy. They rounded 27 to 30, multiplied it by 4, and then took away the 3 extra groups of 4 they had. And the second one, this student did an interesting thing. Basically, they did kind of another type of compensation strategy where they basically doubled the 5 to 10 and halved the 250, thus getting the same answer here. And the last one as well, we see a student that, again, used a type of compensation strategy to round that 17 to 20 and then take away those 3 extra groups. All right, so let's change to look at algorithms here now. Just helpful ways that are quicker and efficient sometimes. But it's only, again, one way to do it. It's not the only way to do it. So let's look at 15 times 24 to get more digits here. And we're going to look at two things that count as algorithms you see in schools a lot. One is using a partial products or the box method, which we've already looked at here, and the second one is just more that traditional algorithm. So let's start with that. And to do that, I'm going to use just some paper here on the side. So give me a second to pull that up. All right, and where to go? Here it is. Okay, and there it is. All right, and so we're going to look at 15 times 24, and we're going to be looking at just algorithms to be able to do that. So let's start with the first one, and we're going to call it kind of a partial products, or kind of a box method. And it's the same thing as the break apart method. We're just going to do it in 2 dimensions now. So 2-digit numbers, we basically are going to take a look at it and realize that 15, again, we could partition into a 10 and a 5 by place value, and the 24 into a 20 and a 4. So we always start just by place value partition. And just like the break apart model, which really is the same thing, we're just going to cut it into sections. It's like an area model without worrying about the proportionality of area, but then basically we have this in 4 sections here. So 20 times 10 is 200. Again, it's just a 2 with 2 zeros. And 20 times 5, again, that's just 10 with the extra 0, that's 100. 40, and 4 times 5 is 20. And so again, basically, what we're left with in our box here is we just need to add those up, and we could maybe do that mentally, 200, 300, 340, 360, or we could line them up and add them up. But basically, we get that 360 there. It's interesting, basically, if we want to look at more of a true area method, if we compare that to our base 10 grid paper from before, I just want to make a connection here just to see how that compares here. If we looked at 24 times 15 here, again, what that might look like is starting with the 24 here and coming down to 1, 2, 3, 4, the 15 over here. And again, I think color is helpful on here, is we have more of a true area model of 24 times 15 that looks like that. And like before, if we were to look at each section, it makes it easier to count. We know each of these full boxes is 100. This one was 5 groups of 10. This one here was 5 groups of 10. This one here would be 20, and this one here would be 40. just if we look at it, we see a connection, between the numbers up here. Again, we see the groups of 200 right there, and here's the group of 100 and the 40 and the 20. What, I should have done it the same way, but that's okay. We get the idea here. It's really the same thing. It's just this one is not proportional and kind of done in larger chunks here. So this is a nice algorithm because it works the same every time. It's visual for the kids. It doesn't hide place value. It focuses on kind of whole number parts. And so that's often where some curricula starts. Of course, we can compare that to just another algorithm that is often used, which is the traditional algorithm. And if we're doing 24 times 15, we know again that it's just a matter of here. What we do is it ignores place value, which is why sometimes it's a bit mysterious and goes through. But we say things like this, 4 times 5 is 20. And then over here, we kind of say ignore that 2 up there, and 2 times 5 is 10, and add that 2, and we write 12. But again, as teachers, we know that really what's happening here is this is really different here. This is 2 10s times 5 1s, and that was really 2 10s up here. So when we're doing that, when we say 2 times 5 is 10, that actually means 10 groups of 10, and this is 2 more groups of 10. It really means 12 groups of 10. But of course, the algorithm kind of hides that just to make it more efficient. So it says 2 times 5 is 10, plus the 2 is 12. And then often, it, kids say, well, we've used that, so, let's get rid of that or erase it. And then the second line, often there's that magical 0. We go to the second line, we have to put in that 0. Well, why is that? Why do we start the second line with a 0? And that's because when we move to the 1, that's really not a 1, of course. That's really a 10. And anytime you multiply by 10, it's always going to end in a 0. So that's why that 0 goes there. And that's a good thing to talk about. I mean, don't let it be mysterious. Just let kids know what's being hidden, so why that's really there. And then we just carry on the process. 4 times 1 is 4. 2 times 1 is 2. And again, if we combine that, we get our same answer. And we can see here that's very quick and sufficient. It's a helpful way to multiply, but we do see that's the pro. But the con is, well, it's a bit mysterious. Why do we do that? Why do we carry a number over? Why do we cross it off? Why do we put a 0 there? So again, there's pros and cons to different methods here as we look at it. And again, when we make the connection, we can kind of see again that there's a connection between the standard algorithm and the area model as well. Of course, the numbers show up in different ways, but we can see how, when we put those together, we can kind of make those connections of how those two relate together. All right, let me pull back here to our slide. I think I'm going to leave it like this. Yeah, so that's what we just looked at. So let's look at a new problem for you to play around with for a second, okay? So I'd like you to take a look at 27 rows of 13 students in each row and to play with this on your own to get a little practice here. So for you, you can pause the video, and I'd like you to maybe try using the base 10 grid paper if you have it there that you printed off. That'd be good to look at, start there. Then try some different reasoning strategies. How might you partition it? How might you use compensation? What would those kind of look like here, maybe to do that? And then to solve using the two algorithms, just to go through it, a box method and the traditional method. Okay, so go ahead and pause it and play with that and kind of write that in your notes just to get some experience and think as a teacher how you might talk through some of the language around that, okay? Pause. All right, so good. Hopefully you played with that a bit and had a chance to try that out. So the other thing I want to talk about is a different algorithm here, to look at here. And this one that maybe some of you learned as well in schools. And again, some curricula and some schools, this is a newer standard algorithm that some schools learn, and it's really how some kids learn to do it. And that is the lattice method. So let's take a look at that. It's just a different algorithm that gained in popularity over the past decade. And so let's take a look at that. All right, so that is right here. And The lattice method always begins the same. It begins looking like the box method, but it's not the box method, and we'll see the very important differences here. Because first of all, it doesn't really show place value. It shows 24 and 13, but just the digits coming down. It always goes across the top and down the right side, always. And then it does divide it into boxes like that. And then it draws in what often are called chutes, like kind of like slides, and it looks like this. You start in the top corner and you draw down from each thing there, and you kind of make these chutes coming down. And then what this algorithm does is it multiplies each together. But this is important. It might do like 4 times 1 is 4. But you notice there's 2 triangles here. If it's 4, I would just do this, 0, 4, kind of like that. If I do 4 times 3 and it's 12, I would write like that, 12, 1, 2. 2 times 1 is 2, so I'd put 0, 2. And 2 times 3 is 6, so I would do 0, 6. Then what you do is you kind of slide down the chutes. So for example, this chute only has a 2 in it, so I'd put a 2 there. This chute has a 4, 1, and 6, that's 11. So just like the standard algorithm, though, I won't write 11 here. I need to carry a 1 to the next chute, so I put a 1 here and carry the other 1 up here. So down that chute, I do 1 and 2 is 3, and this chute just has 0. And the answer becomes what's left outside the chutes here. And so here we get the answer would be 312 as our answer. And that is the lattice method. Now, it's important to ask why things like this work, what's really happening. And it's all about hidden place value here if we go through and think about it. You know, this 4 is really a 4, but this 1 is actually a 10, just thinking about it here. I'm just going to show that. And this 3 is a 1, but this 2 is actually a 20 here, which is interesting. So like, if we actually wrote these numbers out, like 4 times 10 is that's really a 40 right there is what that is. And this one here, when I did the 4 times 3 is 12, that's really a 10 and a 2. And this 6 here was 20 times 2, that was really a 60. What we see is it's really place value. This 1 is actually, it's coming in the tens place here, because I had 40 plus 10 plus 60 is 110. And that means I would trade in a group of 100 up here. That 1 up here ends up being a group of 100. And this is one group of 10. So that 1 up here is really a 100. And this 2 here is really a 200. And I'm just showing real quick, I mean, I wouldn't do this quickly with students or anything, but it's really just, it's hiding all the place value. And so this chute here is all of the 1s, this chute here is all of the 10s, and this chute here is all of the 100s. And so there are pros and cons to the lattice method. Some students like the visual nature of it and like the drawing, and it works out. It only uses 1 digit by 1 digit numbers when you do it efficiently and go through. But obviously it has a lot of hidden meaning here that goes through. It can get very big if you have larger numbers. Some students draw out the chutes wrong and end up getting confused, and it still involves carrying over. So there's, again, pros and cons to consider with that one. All right, so that is now for you. If you've never tried that before, please stop and try it, because this is important to see if you can do it correctly, okay? Just because as a teacher, you need to know different ways you're going to see in schools that you run into learners. So do 35 times 89, okay? So pause the video and do 35 times 89, and then unpause when you're done. Okay, so, well, we've talked about some different thoughts with multiplication strategies and different algorithms to be aware of and to make sense of. Let's talk about division a little bit here as well. And this often gets a little more interesting for people, some things you may not have thought of before. So let's start with a question. So 3 friends ran a lawn mowing business, and let's say 1 month they made $463 in profit. If they share equally, how much will they get? Well, again, with direct modeling, if we had some base 10 blocks, that would be a great way to do that. We're going to look at 463 split evenly between 3 people. So let's use, we don't have our physical models at home, but we do have our virtual ones. So let's try that out for a second. I'm going to pull that up here, and let's just see what that would look like. I have 4 $400 and $63. So I'm just going to pull out that $463 here. So there we go. There's my 6 tens, and here are my 6 ones. Now, we're going to use money a lot with division here because it helps with place value, and we're going to talk about it in terms of $100 bills, $10 bills, and $1 bills, because that's how our place value system works. Now, if we needed to split this up between 3 friends, what I'm going to do is I'm going to make some piles down here on the bottom of my screen. So each friend could get a $100 bill, right? And so this down here shows they each get a $100 bill. Awesome. But there's 100 left that they can't split up. They can't tear it up. So we need to go to the bank, right? You have to go to the bank and trade this in. And if we trade it in, we could trade it in for tens, right? So if I click it and highlight it, on the left side, there is a button right here that says Ungroup Blocks. And if I hit that, it allows me to ungroup the blocks by clicking on it, and I can start kind of taking this down. So what I can do is just each friend just got another $10 bill there. So I'm going to kind of put it on top so we can see it a bit there, like that. And I can kind of divvy this up, you know, amongst the friends. So they each get that. They each get that. Awesome. Now they each have 3 $10 bills. But I have more $10 bills that I can use here. I'm going to put this right over here so I can see it. I don't know why it's going behind there. Interesting. But then this friend here gets another one here. Now, to be helpful here, I can rotate it using the rotate thing on the side. But yeah, so again, just using the visual blocks here, we can see, you can imagine just if we had the actual blocks to it, that would look like. And do I have enough tens to give one more to each person? Yeah, I still have 4 left. So yeah, I can still keep doing this. So each person can still get another 10. Awesome. So they're getting lots of money here. And yeah, so, all right, so each person has one $100 bill and 5 $10 bills, but there's still this one $10 bill left. Well, again, I can't rip it up, so we go to the bank and we trade it in for 10 singles. So I'm going to click it and click the Ungroup Blocks. And again, when I do that, oops, let me hit that Ungroup Block again. There we go. And so again, I'm just going to give each, make sure I can see it easily, going to give each group one of these. And now each group 2 of those $1 bills. And each group gets another $1 bill. And looks like I have these 4 left over here. So I can give everybody one more. And you get the idea here, but just direct modeling, just again, we see that using place value in a money analogy, each student got one $100 bill, 5 $10 bills, and 4 single dollar bills for a total of $154. And there's $1 bill left over. And if we wanted to go to dimes and pennies, we could. But for now, each person gets $154 with 1 left over. And that would be direct modeling. All right, so let's go on to division reasoning strategies here. There are different reasoning strategies for division, just thinking of place value and going through. But I want to show one in particular that schools are using often, and just kind of an interesting way to look at 463 divided by 3. And the reason this is a reasoning strategy is because it's flexible. There's different ways to do it. It's not the same every time. And so let's take a look at that. All right, so let's see. I need to pull up this. And yeah, so $463 divided equally among 3. This strategy looks like this. It's often called a repeated subtraction strategy. I'm just going to call it the flexible division method here for now. So using the flexible division strategy, it looks like this, and it starts differently. Basically, instead of saying how many times 3 goes into 4, it looks more holistic and says, how many 3s do I know can fit into 463 for sure? And I don't need to get the exact right number, just anything. Do I know it goes in 10 times? Yeah. 50 times? Yeah. 100 times? Yeah. Well, that'd be a good place to start. It goes in 100 times for sure, so I put it over here. Well, if I used 100 3s, 100 times 3 would be 300. I used up 300 things, so $300 so far. So I would see what's left. And if I subtract, I would realize there's still 163 left. And I might say, well, okay, now how many 3s can go into that for sure? And again, there's no wrong answer here as long as it goes in. I could say, I don't know, 50. Yeah, awesome. So let's do that. Let's say 50 goes in. And if I do that, 50 groups of 3 was 150. And subtracting, I get there's 13 left. And again, same question. How many 3s can go into that for sure? 4, okay, because 4 times 3 is 12. I'd use up 12 things, and there's 1 left. Gotcha. So there's not enough. I don't have enough to make another group of 3. So over here shows how many groups of 3 I made. I made 154 groups of 3, and I had 1 left over with remainder 1. And this is called a flexible method because it could be done very differently. You know, like that's not the only way you could do it. Maybe that's an efficient way, but again, if I had done this just on the side here, I could have done it very differently. I could have started with, for example, I don't know it goes in 50 times. Great. So if I started with that, then that would have started me with 313 left. Maybe I said, oh, that goes in 50 more times. Great. So that would take away another 150, leaving me with 163. Oh, you know what? 50 goes in again. So I mean, I could put in 50 more 3s going through there, and that would leave me with 13 left. How many groups of 3 can I put in that for sure? Well, 4. And okay, we see at the end I'm down to, again, 1. I don't have enough to make a group. So again, I look over here, and I just used 50, 100, 150, 154 groups of 3 with 1 left over. Same answer, just a little different way to get it. There are many right ways to do it. And this is just a reasoning strategy because it's focused on making sense of it, and there's lots of ways to do it, and it's a way that you will see used in certain curricula. And again, focuses on place value, focuses on a whole number thinking, and some flexible strategy there going through. So that's what that is. There is a nice app called Quotient Cafe, which is kind of fun online. If you want to Google NCTM Quotient Cafe, I believe this still comes up. For the sake of the video time, I'm not going to do it right now, but there's a nice applet that actually acts it out with kids, which is kind of fun. Feel free to explore it if you wish. And lastly, obviously we probably all know long division. Something that gets taught as a way by hand to kind of efficiently do division by hands. And so let's break that down for a second. But let's do it in a way that is encouraging us to make sense of the long division steps. Because the long division can befuddle many kids as they realize, what in the world are we doing? And just the steps can get confusing. So let's use a context again. Same thing, $463 split equally among 3 friends. What we're going to do is we're going to use base 10 language and using the same 3 questions again and again that you can hear me use them to go through to think about this. So I'm going to pull this back up and let's take a look at this. We're going to look at $463 split between 3 kids. And you may notice I'm leaving a little extra space here because this is a good strategy we can use, and I could use graph paper as well. But I'm going to use what we call place value columns to help make sense of this a little bit, all right, to keep our place values separate. And for the sake of language, I'm going to write the money amounts up top. That 4 actually stands for $400 bills. That 6 stands for 6 $10 bills. And that 3 actually stands for 3 $1 bills. All right, so let's talk through this for a second. Now, starting this off, it's a little new at first if you want to talk about this in terms of a context, so I want to just emphasize this. I'm not going to start by saying how many times does 3 go into 4, because that's the traditional algorithm language. It doesn't really make sense in the terms of a context. What does make sense is to start with the money. I have $400 bills, right? How many could each of the 3 friends get? Well, each friend could get $100 bill, right? Yeah. Okay, then second question is, well, how many did you just give away? Well, I just gave away 1 times 3, $300 bills. How many $100 bills are left? Well, 1. Great, so that's where we start. Now, I know I can't just tear up the $100 bill, so I need to trade it in for the bank. And trade it in for what? For tens. Now, I'm just going to show in the bring down method, we bring down the 6 and we put a 16 here. What that really means is if I trade it in and I included these 6 ones, this means 16 $10 bills is what this would mean. So if I have 16 $10 bills, how much would each of the 3 friends get? How many? Well, they could each get 5. Yeah, and this is where with the algorithm, I got to put the highest number to make this work. So that's why it's an algorithm. We all do the exact same. So if they each get 5 $10 bills, how many did I give away? Oh, I gave away 15. Okay, then how many of the $10 bills are left? 1. Great. But if I have one $10 bill left, well, I can't tear it up. I need to trade it in for ones. So when I bring down the 3, it tells me how many $1 bills I'd have if I traded it in and added these 3 I already had to it. Great. Well, how many of the 13 $1 bills would each of the 3 people get? Let's see. Well, 3 goes in there 4 times. Yeah, so they'd each get 4 of those $1 bills. How many did I just give away? 4 times 3 is 12. Oh, I gave away 12, and that means there's one $1 bill left over. Oh, so each of the 3 friends got $154. One $100 bill, 5 $10 bills, 4 $1 bills, and there's still $1 left over there at the end that, again, we will talk later, but for now, just remainder 1 as it goes through. And that's a way to think about the standard algorithm making sense. And I find working with students that a money analogy and just talking through it slowly, helps us to make sense of what's happening. And it's a scaffold. And after we make sense of it, we don't need to keep that language the whole time. That slows us down, but it just helps us make sense of it. I worked with one special ed student once who was a 6th grader, really struggling with this, and he used the word funny. He was doing regular long division and just said, Adam, this whole thing is just a bumble. I think is what he said. It was funny. And so he said, it doesn't make sense. It doesn't make sense. And so we just slowed it down and talked about money and went through it. And once he kind of got what to make sense of it, he then accepted it and very quickly started having much more success just speeding up the process after we had slowed it down and made sense of it with him and used that money context and the bank context for him. So just helpful as a teacher to know different ways of language to do that, okay? And that's what we see right there. So now in that, I just want to show that, just for the side note, Van de Walle offers something in his book that, and as you look at the chapter, he calls it the explicit trade method. And it's really interesting. It's a different way to record the standard algorithm, which actually makes a lot of sense, but I'll be honest, not a lot of curricula use it, but I think it is deserving of a head nod here. And I just want to show what that looks like here as we go through. So here we see the traditional way to record it. If we go ahead and look at Van de Walle's kind of, quote, explicit trade method, it's just a way to record this that makes, a little place value sense. And so let's take a look. It starts off the same, 463, and we're going to divide this amongst 3 workers. I'm still going to put in my place value columns. Again, if you have graph paper, it has it for you. And just for the sake, I'm going to, again, for the sake of language, and I encourage you to do this too if you're doing this method, is to write down the dollar bills up top. But here's the difference. It just starts the same. There's $400 bills split between 3 people. Each person gets $100 bill. I gave away 3 of those, and there's $100 bill left. But here's the difference. It's in the trading for the bank. Instead of just bringing down the 6, it says, well, let's trade it in, because cross it off. I traded in a $100 bill, and when I traded it in for 10s, if I put it there, it tells me I have 16 $10 bills. That actually makes more sense, doesn't it? How many can I give to the 3 people? Each person could get 5. So I just gave away 15 of those bills, which would leave me with 1 $10 bill. And again, the explicit trade here says, well, let's trade it into the bank. So cross it off. I'm trading it in and put it here because that means I'd have a total of 13 $1 bills now because I traded it in for 10 singles. How many can the 3 people get? They could each get 4 singles. I gave away 12 singles. There's 1 single left, and I get the same answer. But you can see how it's interesting how in this type of talking, it makes a lot more sense in terms of the place value. And this is what Van de Walle calls his explicit trade method, and a very interesting way to record the algorithm a bit differently. All right, so that's a head nod to that. So for you, this takes a little bit getting used to. If you were in class, I would have you turn to each other and practice a few on each other, but it helps to just see this one more time. So let's do it together. I'm going to model it one more time together, but see if you can kind of follow along, and then I'll have you try one completely on your own. But I just find this language, teachers, it's new, so it takes a little practice to get used to it. So let's start again. And again, we're going to put in our place value columns. We're going to put in our $100 bill, $10 bill, and $1 bill markings up here. And again, when you start off, remember how I told you to start it off? Don't say, how many times does 4 go into 5? If I want to make sense of it using this method, I need to start with, I have 5 $100 bills. How many can each of the 4 people get? They could each get 1. Great. How many did I give away? I gave away 4. How many bills are left? 1. Okay, great. So I need to trade it in. And I'm just going to do the bring down method for now. But so if I trade it in, that would leave me with 13 $10 bills. Great. How many could each of the 4 people get? Well, that goes in 3 times. They each get 3 of those bills. That means I gave away a total of 12, and there'd be 1 $10 bill left over. All right. So again, I got to trade in that bill. When I trade it in, I'd have 18 $1 bills to use. How many could each of the 4 people get? Let's see, 4 goes in there 4 times, so they could each get 4. That means I gave away 16 of them, and there'd be 2 $1 bills left, and that'd be my remainder. So each person got $134, and there's $2 left over that we're going to need to split up differently. And again, that's just the language that uses that to go through. So your turn for a second. Why don't you pause the video and play with this for a second, all right? I want you to look at $474 split between 4 kids equally, and go ahead and just play with it for a second. Do the following: record it using the traditional or explicit trade method, but while you're doing it, use the place value columns, put the dollars, and try and talk out loud. If you were in class, that's what I'd have you do. Talk out loud while you do it. Practice the language. You have to practice it just like kids have to practice it. So practice the language going through using base 10 language each step of the way. And then when done, try that flexible approach. Try that I showed you, the flexible approach that we did earlier on that question, okay? And if you want, try another one as well. And this can be in your notes that you might take a picture of later. So pause the video and try those out. All right, well, hopefully in trying that, you got to try some of the language and try it out. And in the ACE this week, the homework, you have a chance to, with your group, just make sure you all kind of check each other.